Hello everyone, in today's video we'll be seeing this question from the year 2023. So we have to define the Joule-Kelvin coefficient and we have to write the mathematical form and then determine the Joule-Kelvin coefficient for van der Waals gas, and we will see the Joule-Kelvin coefficient for ideal gas or perfect gas also, and then we will obtain an expression for temperature of inversion, and then we will discuss the cases under which heating or cooling is produced. So let's start. Before starting, I want to share that mechanics handouts are available now. You can buy. So to buy, click on the link in the description box. So let's start the Joule-Kelvin coefficient topic. So this all started with a porous plug experiment. So in this experiment, a highly compressed gas is continuously forced at constant pressure. P1 is greater than P2. A highly compressed gas is continuously forced at constant pressure to expand it adiabatically. The cylinder is isolated from the surroundings. So the heat exchange is zero. So porous plug has number of fine holes, as you can see. Before allowing the gas to pass through the porous plug, it is pre-cooled to particular initial temperature T1. So pressure on opposite sides of the porous plug are kept constant, that is P1 and P2, and we know P2 is less than P1 by moving the pistons at appropriate rate. Suppose the expansion takes place from a constant high pressure P1 to constant low pressure P2. Let the temperature on two sides be T1 and T2. So because the gas is moving from P1 to P2, there is a decrease in pressure. So due to decrease in pressure, the gas expands while it passes through the large number of narrow holes in the plug. So in this process, the molecules of gas are gradually pulled apart. This process is known as throttling process. So now using the first law of thermodynamics, which is dq is equal to du plus PV, the work done. Now we know our process is adiabatic. So the del Q, the heat exchange, is zero. So we can put this 0, and this the initial internal energy, as we can see here. There's the U1 and U2 are the internal energies of the two sides. So the del U is U2 minus U1, and similarly we can write the P2 V2 minus P1 V1. So we can write this in this form also, and we know the enthalpy, that is H, which is equal to U plus PV. It's the sum of internal energy plus PV, the product of pressure and volume. So we can write this as H2 is equal to H1. So we can say that delta H is 0, the change in enthalpy is 0. So the Joule expansion process is isenthalpic. That means the enthalpy is not changing. So now we will be doing the first part. We are going to define the Joule-Kelvin coefficient first, and then we will see the mathematical form of it. So the Joule-Kelvin coefficient is defined as the change in temperature with pressure, and since the expansion is isenthalpic, so we can write the mu as del T over del P at constant enthalpy. So the Joule-Kelvin coefficient, we will represent this with mu, and now we will write the enthalpy as a function of temperature and pressure. So we can write dH. The change in enthalpy can be written as del H by del T at constant pressure dt, and this is del H and del P at constant temperature and then dP. So this is the differential. Now we know the dH is 0, and we know this del H by del T is nothing but Cp. It's the heat capacity at constant pressure. So we can simply replace this with a Cp, and now we have to find dH by dP at constant temperature. So now let's see how to find it. So now to find this del H by del P at constant temperature, we will use the Maxwell equations. dH is equal to TdS plus VdP. Now we will differentiate this whole equation with pressure at constant temperature. So temperature is constant, so this will remain same, del S by del P at constant temperature, this V del P by del P at constant temperature. So this is 1. So del H by del P at constant temperature is T. We will use the Maxwell equation. This del S by del P at constant temperature will be minus of del V by del T at constant pressure, and we will replace this del S by del P minus of del V by del T at constant pressure plus V. So we will put this del H by del P in this equation. So dH is equal to Cp dt plus minus T del V by del T at constant pressure plus volume. This is the dP. Now we will put dH is equal to 0 because it's an isenthalpic process. So 0 Cp dt plus V minus T del V by del T at constant pressure, and this is dP. So we can write this dt over dP as 1 over Cp, and this is T dV by dt at constant pressure minus V, and we know this is at constant H because we have put dH is equal to 0, and we know this the change in temperature with pressure at constant enthalpy is nothing but mu. So this is the mathematical form of Kelvin coefficient. So let's move to the cases. Firstly, we will see the Joule-Kelvin coefficient for ideal gas or perfect gas. And we know the ideal gas equation, this is PV and RT. We have to find the del V over del T at constant pressure. We can rearrange this equation. So we can now differentiate this equation with respect to temperature, and we will get nRT del T over del T at constant pressure. This will be 1. So this is a constant. This is nR over P. We will put this in this equation of mu. So we will get 1 over Cp. This is T. This is nRP and minus V. We can write nRT over P as V from this. So this is 1 over Cp V minus V, which is equal to 0. So mu equal to 0. So in case of ideal gas, no heating or cooling is produced on Joule expansion. Now we will see for real gas or van der Waals gas. Firstly, we will write the real gas equation, which is P plus A over V square. This is V minus B, and this is RD. Now we have to find del V over del T at constant pressure for the real gas. So we have to differentiate this whole equation with respect to temperature at constant pressure. So we will get this is minus 2A over V cube del V by del T, and the second term as it is, then plus P plus A over V square as it is, and the differentiation of second del V by del T at constant pressure, and this will be R del T over del T at constant pressure. So this is 1. So we will take this del V over del T at constant pressure out, and we will get minus 2A over V cube V minus B plus P plus A V square, and this is equal to R. Now we can replace this P plus A V square as RT over V minus B. So the expression for del V over del T at constant pressure will be R over RT V minus B minus 2A V minus B over V cube. So let's move to the next page. So this is RV minus B. This will become RT minus 2AV minus B ka whole square over V cube. So we can write this V minus B square as V square. So we can approximate this V minus B square equivalent to B square. So del V over del T at constant pressure will become RV minus B RT minus 2AV square over V cube. So this will cancel this. Now we'll take RT common from the denominator, and we are left with 1 minus 2A RTV. So we can cancel this R. So we will take this T del V over del T P on the other side, and this is V minus B, and this 1 minus 2A RTV. This is the minus 1 power. So we will use the binomial expansion for this term. So using the binomial expansion, this term will be 1 plus 2A RTV, and we will neglect the higher order terms because A and B are very small. A and B are very small. We can neglect the higher order terms. So we will multiply V minus B and 1 plus 2A RTV. So we will get V minus B plus 2A RT minus 2AB RTV. And we will ignore this term also because the product of two small terms. So we will neglect this product of constants. So we are left with T del V over del T P, which is equal to V minus B plus 2A over RT. Now we will put this expression in this mu. So we will replace this T del V over del T in here. So we will get mu is equal to 1 over Cp V minus B plus 2A RT minus V. We cancel this V and we are left with, so mu for real gas is 1 over Cp 2A over RT minus B. So mu for real gas, and we know the inversion temperature Ti is equal to A over Rp. So we can write this mu in terms of inversion temperature. So we are having this mu for real gas, the inversion temperature. We can write this 2A over R here, and we can replace this 2A over R by B Ti. So this mu is 1 over Cp, this B Ti over T minus P. So we can take this B out. So B over Cp Ti over T minus 1. So it's the mu in terms of inversion temperature. Now we will see the case 1. We know P2 is less than P1 and this delta P, which is equal to P2 minus P1, is less than 0. So delta P is less than 0. We will further divide the cases. If A is very greater than B, then this term 2A over RT minus B will be positive. So that means our mu will be positive, and we know mu is delta T over delta P, and we know for delta mu to be more than 0, and if we know delta P is less than 0, delta T must be less than 0. So in this case, if delta T is less than 0, that means T2 minus T1 is less than 0 and this T2 is less than T1. So that means temperature on the other side is less than the initial temperature. So for positive mu, delta T is less than 0. That means cooling is produced. Then we will see the next case where the B is very greater than A. Then this term 2A over RT minus B is less than 0, and then our mu is less than 0, and we know delta P is less than 0. So for mu to be negative, and we know mu is delta T over delta P, for our mu to be negative and this is negative, this should be positive, then delta T must be positive. So delta T should be more than 0. So that means T2 is more than T1. In this case, heating is produced. So now let's see the last case. At T is equal to Ti, inversion temperature. Then we know the expression for mu in terms of inversion temperature. Now we'll replace this T with Ti only, and we will see, because we are at the inversion temperature, minus 1. So this will cancel and we will get 1. So it's 1 minus 1, 0. So mu is 0 at inversion temperature. At inversion temperature, no heating or cooling is produced. So this is the temperature inversion. At this point our mu is 0. As we go above this temperature, our gas will heat up. As we go down this, the gas will cool down. These are the cases for the real gas. We have completed the whole topic of Joule-Kelvin coefficient. If you have any doubts related to any part of this topic, you can ask me in the comment box. And if you like this video, please like, share and subscribe to my channel. And thank you for watching this video.